Okay, welcome to Chapter 5. We're going to be exploring radical expressions and equations. So the first thing, we got to get some practice working with radicals. So here's your warm-up. Simplify each of these below. So root 25, 5, 11, cubed root of 27 is 3. The root of a fraction, you can take the root of the numerator and denominator independently of one another. So this will end up being 6 over 7. And then e, like I said, we look for numbers like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. All these perfect squares, we see if any one of them can come out of a radical that can't otherwise be expressed as rational. And 25 will come out of this one, so we write this as 25 times 2. And we can take the root of 25, so you can see that this is still 50 under the radical sign. And the root of 25 is 5, so we get 5 root 2. Alright, so here's what we'll be doing. Converting between mixed radicals and entire radicals, so that's what we just did on part E there. Comparing and ordering radical expressions, so just seeing what their sizes are. And some other things. Look at the cardboard box picture below. It is designed to safely transport 15 bottles that each have a diameter of 4 inches. Determine the diagonal length, corner to corner, of each individual bottle storage space, as well as the diagonal distance of the entire box. So they each have a diameter of 4 inches, meaning this distance here is going to be 4 inches, and this distance here is going to be 4 inches. So each of these squares is 4 inches by 4 inches. Now, if we want to figure out the length of the diagonal, we have 4 and 4 in a 90-degree triangle. And this diagonal, we could call it C for the hypotenuse. C squared equals 4 squared plus 4 squared. And C squared equals 16 plus 16. C squared equals 32. C equals root 32. C equals the root of 16 times 2, and therefore C equals 4 root 2. So that is the length of a single diagonal for root 2. Now, it'd be nice if we could just count the diagonals to go across the whole box, but it doesn't work that way because it's not a perfectly square box, it's rectangular. So we have to go all the way across from corner to corner like this instead, meaning we have to do the exact same thing that we just did, but for the entire box. This time for the width and length, or width and height if you want to look at it that way, of the entire box. So this is 4 inches plus 4 inches plus 4 inches. So that's 4 inches times 3 is the height, which is a foot. And across we have 1, 2, 3, 4, 5 squares, and we have 4 inches times 5 squares, which is 20 inches. So we now have, again, a right triangle, because this corner is right. And this is 12 inches, and this one is 20 inches. So this is C. And again, we can calculate C using Pythagorean theorem. C equals 12 squared plus 20 squared. Sorry, C squared equals 12 squared plus 20 squared. C squared equals 144 plus 400. C squared equals 544. And C equals the root of 544, which is 23.32 inches. There you go. Read textbook page 273 and answer the following questions. I'll leave you to that. Your turn, page 274, your turn number 1. Convert each mixed radical to an entire radical. So this is doing the opposite of what we did in the warm-up in part E. So this one, 4 root 3, we actually want to put the 4 under the radical sign to mix it with the root 3. Now, if it's a 4 outside of the root, that means it's already had its root taken and it ended up being 4. Anything we want to move to under the root, we have to square it so that we don't change it. So 4 outside of the radical is the same as 16 inside of the radical. And if you're unsure, just see what it would look like if you went the other way. Root 16 would be 4, and we would move that outside of the radical. So it's the same thing here, and this would be root of 48. So now it's an entire radical. J cubed times root j. If we want to move j under the radical, we have to square it. Sorry, j cubed under the radical, we have to square it. J cubed squared is j to the 6, so you multiply your exponents here when it's the power of a power. So move it under the radical, it would be j to the 6 times the j that already exists under there, which would leave us with the root of j to the 7. Similarly here, except now we're taking the cubed root. So if we want to put this under a cubed root, we have to actually cube this whole thing in order to get it under the radical. So 2 cubed, cube that whole thing, 2 cubed is 8. K squared cubed is the power of a power, so 2 times 3 is k to the 6. That's to get it under the radical. Sorry, and this is a 3 cubed root. And of course multiply it by the 4k that's already there. And cubed root of 4 times 8 is 32. K to the 6 times k is k to the 7. Cubed root of 32k to the 7. We're done. A radical is in its simplest form. If the following is true, you can find these notes in your textbook. We'll move on to the your turn here. We're going the opposite way now. Express each entire radical as a mixed radical in simplest form. Identify any restrictions on the values for the variables. No variables in this one. Root of 52. Will any perfect square come out of 52? Well, 4 will definitely come out of 52, and it will leave us with the root of 4 times 13. The root of 4 we can express, move it out of the radical, and we get 2 root 13. Now the fourth root of m to the 7. This is a weird one because we're taking the fourth root, but m to the 7 can be written as m to the 4 times m cubed. Okay, when you multiply powers with like bases, you add their exponents. So this would be m to the 7. Now the fourth root of anything to the 4th just leaves us with whatever the base was. So we take the fourth root of m to the 4th, that just leaves us with m. Of course, the m to the 3rd is still trapped underneath the radical in there. And there we go. Fourth root, this is an even numbered root. We cannot take the even root of a negative number. and therefore the restriction on the variable is that m must be greater than or equal to 0. Because if we take a negative number to the power of 7, we end up with a negative number, and we can't fourth root a negative number. Alright, 63, n to the 7p to the 4. There's a lot going on here. Let's deal with the 63 first. 63 can be written as 9 times 7. Alright, n to the 7 can be written as n squared times n squared times n squared times n. P to the 4 can be written as p squared times p squared. The reason I'm choosing to break it down into little squared bits is that we are taking the square root. So here we are taking the fourth root, so I busted this into a 4 power of 4. Here we're taking square roots, so I'm going to bust everything into a square that I possibly can. So first let's take the square root of 9, which is 3. We move it outside of the radical. The 7's got to stay because it's prime. The square root of n squared is n. One of them done. Square root of n squared is another n outside the radical. Two of them done. Square root of n squared again is a third n outside of the radical. This n stays because we don't have two of them. We don't have enough to square root. Square root of p squared is p, times p, and the square root of p squared again is p. Under the radical, what's left is 7n. So we rewrite this 3n cubed p squared root 7n. And we're taking the square root. So if n was a negative value, n to the 7th would be negative as well. Can't square root a negative, so n must be greater than or equal to 0. P to the 4th, on the other hand, if p was negative, p to the 4th would be positive. So it doesn't matter if we throw negative values in here for p. It will always end up positive when you raise it to the power of 4, and we will always be able to take the square root of that. So there are no restrictions on p. P is an element of the reals. It can be anything you want it to be. Now there is a quicker way to do this. If you want to take a shortcut, I'll just show you quickly. N to the 7 can be written as n to the 6 times n. And if we're taking the square root of something like this, any even number, you take the square root of something to an even power, and it will just have that number. So n6, you take it out, becomes n cubed, and just n would be left. Similarly with p to the 4th, you have that power, and it comes out as a p squared, and there would be nothing left there. Okay, so that's a quicker way of doing this, but if you can't see it, don't stress about it. This way will always get you to where you need to be. Alright, your turn number 3. Order the following numbers from least to greatest. I find this is easiest just by writing them all as an entire radical rather than mixed radicals. So I'm going to rewrite all these ones that are mixed. So I'm going to put the 3 under the root sign, and this is going to be root 9 times 3. Okay, the 3 can't just go in there as a 3 and multiply by 3. We have to square it first. So this becomes a 9, and we still multiply it by 3. So this would be root 27. This one, 2 root 6, we want to move the 2 in, so we have to square it. So that's the root of 4 times 6, and that will be root 24. This one's root 23. And this one, of course, there is no radical, but we can turn it into a radical if you square it and put it under the root sign. Square 5. 5 is the same as root 25. So now it's really easy to see what order these things should go in, because they're all different sizes. Order them from least to greatest. So root 23 was our smallest. Then root 24, which started out as 2 root 6 was our next smallest. Then root 25, which just started out as 5. And then root 27, which started out as 3 root 3. And that's how we order those. We rewrite them all as entire radicals. Okay, simplify radicals and combine like terms. If they have the same radicand, which is 7, and the same radical index, which is 2, which means it's the square root, then we can add them. It's like 2 apples plus 13 apples. So think of that root 7 as an object, and it has to be identical in every way. So the square root of 7 and the square root of 7. So if we have 2 of them and we add 13 of them, we get a total of 15 root 7s. Here, this one looks a little different, but we know that we can rewrite 24 as the root of 4 times 6. And then we can evaluate the root of 4, which is 2, move it outside the radical. Now we have 2 root 6 minus 1 root 6, or 2 apples minus 1 apple, which would leave us with a single root 6. Alright, now one that requires a bit more work. 20 can be rewritten as 4 times 5, and of course that x is still in there. We can evaluate the root of 4, which is 2, so this is left as 2 root 5x. Now this one, 3, and under the radical sign, 15 times 3 isn't going to get us anywhere. And actually 45 does not have a perfect square that will come out of it. Oh yes, it does. 9 will come out of it. So 45 turns into 9 times 5. 9 is the perfect square. 9 we can take the root of, and it becomes a 3 along with that other 3, and it's gone, and all we're left with is root of 5x. So now, even though they looked completely different at the start, we've turned them both into one of our apples, I guess you might say. So this is 9 root 5x. So now we have 2 root 5x minus 9 root 5x, so 2 apples minus 9 apples, which would leave us with negative 7 apples, which root 5x is our apple. And that's that. Oop. Okay, last page. What is the exact length of AB? AB is this length across the bottom right here. When we're asked for an exact length, that means no decimal numbers. It has to be expressed as a perfect radical or rational expression. In this case, it's going to be radical. We know from our experience with 45, 45, 90 triangles that this, the hypotenuse, we go 1, 1, and this is 1 root 2, or whatever the leg is, times root 2. Now, root 12 we can rewrite as the root of 4 times 3, which will give us 2 root 3. So that's not really going to help us here because we were hoping for something root 2. So we could just write this length as a nice whole number, but that's not going to be the case, so we got a little more work to do here. So the hypotenuse, this side is going to, let's call it A, this little length here, and A is going to be this height because these are going to be equal in a 45, 45, 90 triangle. So we go 2 root 3 squared equals A squared plus A squared, which means 2 root 3 squared equals 2a squared. 4 times 3 equals 2a squared. 12 equals 2a squared. Divide both sides by 2. 6 equals a squared. A equals root 6. Now that's just this length here in green. We still have to find this length here in blue with our 30, 60, 90 triangle. But again, we can use Pythagorean theorem. Similarly, well, this one's going to be a little trickier. Our 30, 60, 90 triangle usually goes like this, 1 and 2, and then this one is root 3. In this case, we have taken our hypotenuse and multiplied it by root 2 to get this, meaning we can multiply every side by root 2 because they will all scale up to the exact same proportion, and that will give us the length of each one of the sides of that triangle. So the long edge of the triangle is going to be root 3 times root 2, and here it's the root of your product of your two radicands, which is 3 times 2, which is 6. So this one is also going to be root 6. Obviously these haven't been drawn perfectly to scale, so A is root 6, and this little length here, we'll call it B, is also root 6. So the whole length of AB then is root 6 plus root 6, or an apple plus an apple, which is 2 apples, 2 root 6s. That's it for today. See you in class.